What is a polynomial? A polynomial is an expression with many terms. That's what poly means. There are several different types of polynomials. There's the monomial. Monomial means one term, so 3x would be an example of a monomial. Binomial, the prefix bi means two, so this would be a binomial. And then there's a trinomial, the prefix tri means three, so this would be a trinomial. There are other higher order polynomials, we just don't have names for them. So if I gave you 2x to the fifth plus 3x to the fourth minus 6x plus 1, we would call this a fifth degree polynomial. And the reason it'd be called a fifth degree polynomial is because the biggest exponent in the expression is a 5. The degree of a polynomial is the highest exponent of any of the terms in the polynomial. So let's look at some polynomials and the number of terms and its degree. If I give you something like 5, there is no x with an exponent. Because of that, we say that this is a polynomial of degree 0. That really means that the exponent of x is 0 and anything raised to the 0 power is 1. This has one term, and if it has one term, it's a monomial. X plus 4. The biggest exponent of x is 1 because it's an x to the first power, so we say that this is a polynomial of degree 1. It has two terms, so it's a binomial. 4x squared. Its biggest exponent is 2, so it's a polynomial of degree 2. It only has one term, so it is also a monomial. So as you can see, a monomial just means one term. It doesn't matter if it has an x or if that x is raised to a power. 4x cubed minus 2x squared plus x. That's degree 3. It has three terms, and it's a trinomial. 2x to the fourth plus 5x squared is a polynomial of degree 4. It only has two terms, so it's a binomial. The same thing applies as did with a monomial. It doesn't matter how many terms it has. The degree only depends on the biggest exponent. The last one here, negative x to the fifth plus 4x squared plus 2x plus 1. The biggest exponent is 5, so we say it's degree 5. It has four terms. It doesn't have a special name. We just call it a polynomial of degree 4, or the book calls it polynomial of 4 terms. Any of those should suffice. When we write polynomials, we like to write them in something called standard form. Standard form of a polynomial is when you write the polynomial in descending order of powers, or if you arrange the terms by degree in descending numerical order, i.e., you put the term with the biggest exponent first and everything goes down from there. Let's actually write some polynomials in standard form. So this first one, 3x plus 9x squared plus 5. The term with the biggest exponent is 9x squared. The next term with the biggest exponent of x is 3x, and since it's positive, I'm going to write it as plus 3x. The constant term, the one that doesn't have a variable, is always going to come at the end. So I have a polynomial of degree 2, because 2 is the biggest exponent. It has three terms, and is therefore a trinomial. In the second problem, 4x minus 6x squared plus x to the fourth plus 10x squared minus 12. The term with the biggest exponent is x to the fourth, so that gets written first. The next biggest exponent is 2, but there are two terms that have x squared. Well, we have to combine them. So negative 6x squared plus 10x squared is positive 4x squared. The next term with the biggest exponent of x is 4x, and it's positive, so I write plus 4x. And the constant term minus 12 just gets written at the end. This polynomial is degree 4 since it's the biggest exponent. It actually has 4 terms, not 5. Remember, we had to combine like terms before we determined what its degree was and how many terms it really had. And since terms polynomials that have 4 terms don't have a special name, you can just call it a polynomial of degree 4 or power 4, or you can call it a polynomial of 4 terms, whichever one works for you. Now let's talk about turning points. In pre-calculus, we'll call these critical points because these points are very important. The turning points are the points on a curve where the graph changes direction. And by changing direction, I mean it was going up and now it's going down, or the graph was going down and now it's going up. So I give you 4 different types of graphs up here. The first one is a linear equation, because linear equations were just straight lines. Linear equations do not change direction. They go in the same direction forever. We say that they have no turning point, no place where the graph changes direction. Quadratic equations, however, when you graph them, you're going down and then all of a sudden you stop and you start going up. And the vertex of the parabola is a point where the graph changes direction. So quadratic graphs have 1 turning point. The next graph is one you have not had to deal with yet. It's the graph of something called a cubic function. Cubic functions are ones whose biggest exponent is 3. Not all cubic functions look like this one. Sometimes they also look like this. But the one that I've drawn in black, if you follow the curve, it goes up and then it stops because it goes down. And then it stops because it goes up. We say that that graph has 2 turning points. Now the cubic function that's drawn underneath of it, sometimes it doesn't have those humps in the middle. The one underneath has no turning points. It just continues up forever. The last curve is the curve of something called a quartic function. A quartic function is one whose biggest exponent is 4. Quartic functions usually look like M's or W's. Well, this graph changes direction in 3 different locations. So it has 3 turning points. Now there is a type of quartic function that when you graph it looks like a parabola, in which case it only has 1 turning point. But quartic functions are always going to have some sort of turning point or multiple turning points. Let's go back for a moment to our quadratic standard form. One of the things we learned when studying quadratics was when the leading coefficient was positive, the graph opened up. And if the leading if the leading coefficient were negative, the graph opened down. So you knew kind of what the graph was going to look like without doing any work or even needing a calculator. Well, the same thing holds for other types of functions. For cubic functions, this is just a generic cubic function. If the coefficient in front of a cubic function is positive, the graph will go up from left to right. That's very important to note, from left to right. And if the leading coefficient is negative, the graph will go down from left to right. For a quartic function, anything of degree 4, if A is positive, the graph will go up. However, if A is negative, the graph will go down. This leads us into where do those 2 ends of the graph end up going? This is called the end behavior. The end behavior is the directions of the two ends of the graph, the two ends that seem to go off of the graph, and you can't see them if you graph them on the calculator. Now, remember, one of the things you have to remember when you graph any kind of function on the calculator is that you have to remember that you can only see what's in the box. There is a whole other part of the graph that you can't see just on that screen. So let's go back to our linear graph. This end of the graph is going up forever, and this end of the graph is going down. That's called the end behavior. I'm fine with up and down. However, I'd like to move you into telling me that this end of the graph goes to positive infinity, and this end of the graph goes to negative infinity. Infinity means it goes on forever. So if you say positive infinity, you mean it's going up forever. This quadratic graph, this side of the graph goes up, and so does this side. So in a quadratic graph that opens up, both ends of the graph go up, or in other words, they go positive infinity. However, if I had given you a quadratic whose leading coefficient was negative, both ends of the graph would have gone down, or they would have gone to negative infinity. For the next function, which was our cubic function, this end of the graph goes up, this end of the graph goes down, or you can tell me that this end goes to positive infinity and this goes to negative infinity. For the quartic function, this particular one that I've given you, notice that both ends of the graph go down. Now, in order to tell me the end behavior, what I'd like you to do is I'd like you to draw me a sketch of what the graph looks like. How do you know what it's going to look like? Plug it into your graphing calculator or some other computer program that will graph for you, and then just draw me a quick sketch of what it looks like. It doesn't have to be anything fancy. These two graphs, if you graph them in the graphing calculator, they have the general shape of the two graphs that I've drawn underneath of them. I don't care right now about where the coordinate plane is. We're going to worry about the coordinate plane at another point in time. For end behavior, the only thing I care about is that you tell me this end goes up or it goes to positive infinity, and this end goes down or to negative infinity. That's all you're going to do for end behavior. For the second graph that looks like an upside down M, this end goes down or towards negative infinity, and so does this end. Now remember, end behavior is different from the turning points. These are my turning points in blue. In red is the end behavior. So in order to tell me the end behavior, all you need to do is graph the function and give me a little sketch on your paper, and then tell me where the graph goes up or down.